So till previous session we go through with the SOP and POS stuff, how we calculate the minimum number of gates. Okay, but there are two particularly possible conditions we have to have. One with the minimum number of general gates, those basic gates, and second with minimum number of XOR, NAND and NOR gates. Any doubt in that part, you can ask me. Next, we start with the basically combinational circuits. Okay, so we start with the combinational circuit. So here we discuss two type of combinational circuit. One is the mux of the demux. Second is encoder of the decoder. Mux and demux both are the just opposite process. Okay. Mux, what the mux will be do? It will be combine multiple input in a single line. Okay. Single line. Okay. And what demux do? It will be again convert a single line data to the. So it is a n cross 1 and this is the 1 cross n. Okay. Now, which particularly line will be input line will be go as a output and which particularly input line, which particular data will be go as a output line. For example, from this input line, the data will be go to which particularly output line, and from which particularly input line the data will be go as a output. That all will be decided by the select. And how many select lines? Select line is log 2 of n. Log 2 of n. Okay. So that means if we have a 8 cross 1 mux, so we have a 3 select. If we have a 4 cross 1 mux, we have a 2 select. 2 cross 1, 1 select line. 16 cross 1, 4 select line. And so on. Okay. Similar way, if we are talking about the demux is just opposite to this one. Okay, demux is just opposite to this one. If we have a 1 cross 8, so it is a 3 select line. If we are taking the 1 cross 4, we have a 2 select line. Okay, so the process is just opposite. So demux will be taken as a 1 cross 8, 3 select line, 1 cross 4, 2 select line, 1 cross 2, 1 select line, 1 cross 16, 4 select. Okay. So basically these two devices will be used for the multiplexers. Okay, that's why it is called the multiplexers and demultiplexers. Okay. Now we can design in this particularly mux and demux. We have a three type of problem. One is the from the lower order. to higher order. This is the first type of case. Second type of case is that higher order with less with lower order. Okay. And third is implement any Boolean function using mux. Okay, like for example, if we want to implement a 4 cross 1 using 2 cross 1, because that means we have a 2 cross 1 mux. So two input line, again two input line, common select line, the output that is coming from here and the output that is coming from here. Again go to the 2 cross 1 mux and select line. Okay. This select line is S0 and this select line is S1. So I0, I1, I2, and I3. If I write down the equation for this point is it is a I naught S bar plus I1 S. If select line is 0, if select line is 0, so I naught is selected. If select line is 1, I1 is selected. Similarly for this point, it is a I2 S naught bar plus I3 S naught. Okay, and from here it is again a 0 and 1. So if it is if this one is selected, so I naught S naught bar plus I1 S naught multiply by S1 bar plus if this line is selected, S is 1. So I2 S naught bar plus I3 S naught multiply by S1. Okay, so I naught S1 bar S naught bar plus I1 S1 bar S naught plus I2 S1 S naught bar plus I3 S1 S naught. Okay, so this is the one type of problem. The second type of problem is that we can implement any Boolean functions. Like if y of AB is given, that is sigma m 0 and 3. Okay, so we are choosing the A and B as a select line. Okay, 0, 1, 2, 3. So I naught, I1, I2, and I3. We required I0 and 3. Okay, so it is a SOP term. So what should we do? We just connect a 0 and 3 for short that particular terminals and connect with 1. Connect with 1. Why connect with 1? Because it is a SOP term. It is a SOP term. And both remaining 1 and 2 that will be connected with the 0. That will be connected with the 0. So here we are getting YAB, that is equal to sigma m 03. Okay, that is the problem number 2. Now third thing is that problem 3. If we are having a YAB, that is again 0 and 3, and we have to implement using 2 cross 1 marks. That means 2 input line and 1 select line. We have a 2 inputs A and B, but we can use only one input as a select. Okay. Second input we connect as the input line I naught or I0. Okay, so how we do that one? B as an input, A as a select line. So the value of A is 0 and 1. The value of B is 0 and 1. Okay. So it is a 0 0. It is a defined term 0 0. So here we mark as a 1. 0 1. That is 1 not defined. Not defined. A is 0, A is sorry, A is 0 and B is 1. So that means 0 1. So not defined. It is a B is 0 and A is 1. So 1 0, it is not defined. Last is the 1 1, it is defined. Okay. So we select any of the input as a select line and any other input as an input form. Okay. Now when A is 0, so which line is selected? This line is selected. So A is 0, this line is selected. Now is this line, what is the equation? It is defined only for B is equal to 0. So can I connect as a B bar? Can I connect as a B bar? And when A is 1, this is selected. This is selected. So when A is 1, this is selected. So if this particularly position, if I write the equation, so in this equation only B is equal to 1, it is defined. So it is called the B. So if I connect as a B bar here, and if we connect as a B here, okay. So here we are getting Y A B, that is equal to sigma m 0 comma. Okay, that is the third type of problem. Okay, any doubts? Now, in the similar way, if we are talking about the question y of A, B, C, and D is equal to sigma m 0, 1, 3, 4, 5, and 7. So, let me just take a sequence. 1, 2, 7, 9, and 11. Okay, we have to implement this one using 4 cross 1 marks. Okay, then you have to identify the minimum number of basic gates required. Can you solve it?
So in basic gates, we will use NOR gate and means AND gate, NOR gate, NOT gate.
No, basic gates is basically and, or, and not.
So we will not use XOR and XNOT.
Yeah.
Okay. Yes, sir, it is done.
Okay, so how many gates?
So 5 gates.
5 gates. Which line you are considering as a select line?
I have considered A and B.
Okay, A and B you are considering. Okay. So the thing is that how we define that which particularly select line, gate line, because there is a no, it is not given in the question that which you are considered as a select line, which you are considered as a input line. So there are, if you know that particularly four variables, so there are lots of combination we can create. Okay. So first of all, if we write down that 0 0 0 1 0 0 1 0 0 1 1 1 1 0 0 1 and 1 0 1 1. Okay, so now if I consider that this one, and this one, so let's like assume that A and B is my select line. A and B is my select line. Now if A and B is the select line, the possible value is 0 0 0 1 1 0 and 1 1. Now CD is my input line, that is 0 0 0 1 1 0 and 1 1. Now where it is defined 0 0 0 1. So here it is defined 0 0 1 0, which is defined here. Okay, 7 0 1 1 1. It is defined here. 9 1 0 0 1 1 0 1. Okay, and here it is not defined, so we consider as a 0. It is defined, so we are considered as a CD. Okay, it is defined here, so we are considered as a D. Why? Because C is variable, only D is constant, and it is defined, so where we consider the C, X, or D. Okay, so, four inputs. The last one is a 0. The third one is a D. Second one is a C and D. Okay, and first one is the, if it is a C D bar plus C bar D, so you have to take a 4 gates. C bar, D bar, okay, C connected with D bar, ending, and D connected with C bar, ending, and after that it is a 4. Okay, after that it is a 4. So here we are getting a C XOR D, here we are getting a CD, here only D, and here it is a 0. So how many gates we required?
6 6.
6 gates.
Actually, I have
5
not.
for the,
Actually, I have not considered the OR gate. I forgot.
okay, okay. So basically 5 gate for the XOR, okay, for the first input and one AND gate. So total 6 gates are required. If we are talking only the basic gates, okay, and if there is no limitation of the basic gates only, any gates. Okay, if we consider any gates, so how many gates is required? Only two gates, because we are using directly the C, and D comes from here. It will be go into the XOR. Okay, it will be come to the XOR. So C, D. Okay, so one gate is this one and one gate is this one. So if consider any gates, so two gates are required. Okay,
Yes, sir.
so this is the one type of problem that we consider with the mux. Okay. Any implementation, any particular Boolean expression we can implement using the mux circuit. Okay, demux is just opposite to that one. Demux is just opposite to that one. Mm, demux give you the multiple output. Okay, demux give you the multiple output. So without any gate, it is impossible to implement Boolean expression. Boolean expression. Okay. Now next is the encoder and decoder. Okay. The encoder and decoder, there is no select line. It is somehow similar to the demux or the mux, but the difference between them is that for the mux and demux we required a select line, in this particularly we doesn't require any select line. Okay. Now the decoder is n plus 2 raised to power n, and encoder is 2 raised to power n plus n. Okay. So if like for example we have a 3, n value is 3, so we have a 8 output lines, 8 input lines, and 3 output lines. Okay, and that will be controlled with the enable. That will be controlled with the enable pin. If enable pin is 0, that particularly encoder or decoder circuit will not work. That encoder and decoder circuit will not work. If the enable value is 1, then this particularly encoder and decoder will. This particularly encoder is used to convert any input data into the binary. Like for example, we have a I0 to I7 or yeah I0 to I7, and we don't know what is the binary number of 6. So what should I do? I just apply a 1 on a I6. Okay, I apply 1 on a I6. With respect to this one, we are getting output as 1.0. Okay, so basically encoder do this one. It will be convert any type of data, input data into the binary. Okay, now if it is a 8 cross 3, so we call that octal to binary. Octal to binary. If it is a 16 cross 4, we convert called as a decimal or hexadecimal to binary. Okay, if we have a 10 cross 4, okay, that basically 10 cross 4 is not possible, but we convert a 16 cross 4 into 10 cross 4. Then it is called the BCD to binary. BCD to binary. Okay. Now the decoder is just opposite to this one. If we have a 3 input, so we have a 2 raised to power 3, that means the 8 is out. Okay, so it is a 3 cross. Okay, so it is convert binary value to their respective respective decimal value. Okay, binary value to respective decimal value. Similarly, if it is a 3 cross 8, we call as a binary to octal. If we have a 16 cross 4, we have 34 cross 16. We have a binary to hexa decimal and cross 10. So binary to decimal. Okay. The advantage of the decoder is that we can implement any Boolean expression. Okay, we can implement any Boolean expression. Any doubt? Miss, any doubt?
No, sir.
Okay.
So this lecture will contain week 5 to week 8 content, no? Or
Yeah, around week 5 to week 8.
so will you please cover the adder and subtractor concept
Yeah, okay.
if possible?
Okay, I add. Okay, so adder is what? There are two types of adder is available. One is the half adder and second is the okay. Similarly, if you are talking about the subtractor, so that is again a with the help of a half adder or full adder, we can create a subtractor also. Okay. So in the half adder, we have a two inputs and two outputs. Similarly, for the full adder, we have a three inputs and two outputs. So, like for example, this is our block diagram where we are consider the A and B as a input. With respect to this one, we are getting a sum and carry as a. Okay. Similarly, if we are talking about the full adder, so along with A and B as input, seen as a carry, input carry, we are getting a sum and C. Okay. So if we draw the truth table of that one, so what is the A, B, sum and carry? If both are 0, 0, sum is 0 and carry is 0. 0, 1, sum is 1 and carry is 0. 1, 0, sum is 1 and carry is 0. And 1, 1, sum is 0 and carry is 1. Okay. So what is the carry? Question is that it is a dot B. Okay, because if carry is only in this one this scenario, only with respect to this one. So what is the main term? AB. Okay. Now if we are talking about the sum will be one for these two conditions. One is this one and one is this one. So it is called the A bar B and this is called the A B bar. So sum is nothing but A X. Okay. Similarly, if we draw the truth table for this one, so we are taking the A, B, and C in as input, sum and C out as the output. Okay, so with the three input, we have possible eight combinations 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, and that's the one. Okay, so when all are 0, sum is 0, 1, 1, sum is 0, carry is 1. Sum is 1, sum is 0, carry is 1, sum is 0, carry is 1, and 1 and 1 is 0, carry is 1, and 0 plus 1 is the 1, so sum is 1, carry is 1. Okay. Now if we draw the K map and find the sum expression, A, B, C, N, 0, 0, 0, 1, 0, 0, 1. So sum will be defined at a 1, 2, 4, and 7. You already know this is the equation of A XOR B XOR C. Okay. If you don't know this particularly, so just each term will be individual. Each term is individual. There is no group. So if you write a expression, so it is A bar B bar C in plus A bar B C in bar plus A B bar C in bar plus A B C. So from that one, I am taking as a bar as a common. A bar. So B bar C in plus B C in bar. So it is a B XOR C plus A as a common. It is a B X nor C. Okay. Now assume that B XOR C in is equal to X. So it is A bar X plus A X bar. So it is A XOR X. So that is the A XOR B XOR C. Okay. And if you are taking B X not seen as X, so the equation will be A bar X bar plus AX. So that is the AX more X. So if you put is in the value, so it become a X nor B X nor C. Okay. So for both cases possible. Similarly, if you remember that we already discussed that if three we are talking about three input, so A XOR B XOR C in is nothing but equal to the A X nor B X nor C for the three input only. Okay, if you are talking about the two inputs, so it is A XOR B is just complement of A X. Okay, so your sum equation is what? Sum is A XOR B XOR C or A X nor B X nor C. Now go to your carry part. A, B, C. Carry comes from 3, 5, 6, and 7. So the carry equation is what? There are three groups. 1, 2, and 3. So carry equation is BCN for this group. For this group, we are taking as A, CN, and for the last group we are taking as a okay.
Yes, sir.
Now if we are talking about the subtractor, okay, like for example if we are taking about the a minus b, okay, so basically concept is what is saying that in the digital there is no subtractor, there is no divider, only the possible is the adder and multiplier. Okay, so if I write as a minus b, so I can write it as a plus of minus, okay, and that is nothing but equal to a plus 2's complement of b. Okay, or I can write it as a plus b bar 1's complement plus 1, that is a 2's complement. Okay, so this particularly behave as a subtractor.
Sir, why B bar plus 1?
Why b bar plus 1? Because we know that 2's complement is nothing but how we implement the 2's complement, we calculate the 1's complement and add 1, it becomes is equal to the 2's complement. Okay, now how is the 1's complement, what is the meaning of 1's complement? Just invert, so it is nothing but a invert, and if I am taking with add with the 1, so it becomes a 2's complement. Like for an example, your value is 1011, so what is the 2's complement of that one? Just take a complement, 1's complement, so 0100. Now add plus 1, so 1010. So this is the 2's complement. Okay, how we do that one? Initially 1's complement, and what is the meaning of 1's complement? Just invert. Okay, and add plus 1, add plus 1, it becomes a 2's complement. So that's why I can write a minus b as a b bar plus 1. Okay, is it clear?
Yes, sir.
So that is simply the subtract. Now this is the single bit. Now if we are talking about the 2-bit, 4-bit adder or subtractor, so what is the opinion is that there are, if we are talking about the 4-bit, so what is the possibility that we can implement 4-bit adder? So we are taking the fourth floor. A0, B0. Initially LSB will be added. If carry is given, okay. Carry is not given, we are consider carry is 0. Okay. From here we are getting the S0 and C1. Now that C1 will be used for the input of second bit. Okay. Again add B1, A1. We are getting a S1. Here we are getting a C2. Now use this C2 with the input of this one. B2, A2. We are getting a S2, C3. B3, A3, S3, and finally C1. Okay, so we can implement 4-bit adder using 4 full adder. Okay. Now second way is that if carry is C in is not given, if C in is not given, so what should I do is that first particularly adder I use as a half adder. Why half adder? Because C in is not given. So we have a B0, A0, that will be given me the S0, okay, and C1. Now that C1 will be used for the second. Okay, so we can implement this with the help of 3 full adder and 1 half. Now the thing is, why half adder? Okay, what is the benefit if we are using the half adder and we are not using the full adder? So the benefit is that if you are talking about the half adder and full adder, you go with the equation part. Okay, so half adder it will be implemented with 2 gates. Okay, one is the XOR gate, 2 input XOR gate, and second is the AND gate. But if you are talking about the full adder, so if you see that we for the sum we required a two input XOR gate. Initially A XOR B is done, then output will be done with the C XOR C XOR with C. So first XOR gate is for this one, and output will be XORing with this one for 2 input XOR gate. Similarly for the carry, one AND gate, one AND gate, one AND gate, OR gate, and then again OR gate. So total 1, 2, 3, 4, 5. 5 gates is for that one. So 5 gate for this one, 2 gate for this one. It was 7 gate is required. Whereas in the case of half adder, we required only 2 gates. Okay. So if we required a implement, if C was not given, so first stage we are using as a half adder. The only benefit is that in the case of half adder, the number of gates is less. If the number of gate is less, propagation delay is less. Okay, circuit complexity is reduced less. Okay, so that's why. So there are two options that we can implement a 4-bit adder using a 4 full adder or 3 full adder plus 1 half. Okay. Now I give you the one question. Uh, Okay. Before that one, we go with the comparator. Comparator. What the comparator do? Comparator is basically compare two inputs. Either it is a 1 bit, either it is a 4 bit. We will compare the two inputs. So if we are giving the two inputs, 1 bit inputs B0 and A0, with respect to this one, we are getting it two or three outputs. One is if A greater than B, A equal to B, and A less than B. Like for example, B is 0, B naught is 0, and A naught is 1. Okay, so that means A naught is greater than B naught. Okay, A naught is greater than B naught. So here we are getting as a 1, and these particular two pins we are getting as a 0. Okay, so that comparator circuit will only compare the two inputs. The input is 2 bit, 1 bit, 3 bit, 4 bit. That is according to our requirement, but it will be compared the input. Is it clear?
Yes, sir.
Now the question is that
So similarly for the multi-bit, no, it's- as
yeah, for similar for the multi-bit. Like for example, if we have a 2 bits are there. Okay, B naught, B1, A naught. Again, we are getting every time we are getting a three output. A greater than B, A equal to B, A less than. Okay, so like for example, we are getting a 1 0 and 1. Okay, 1 0 and 1. So we know that B is greater than A. B greater than A. So here we are getting a 1, and for B, these 2 points we are getting a 0. Okay.
yes, sir. So
Now
for
the question is, yeah.
uh, when the multi-bits comparator or the adder comes,
Mhm.
the questions are twisted a little bit, and we have to solve it. You know, we have to express in terms Boolean expression and draw the corner map, and then we have to do that.
Yes, yes,
So,
yes.
like, what is the technique to solve that sums? Because it's
Uh,
confusing to solve.
which confusion? Like if
Means
you
in
give any
case of,
question, like what is the equation for?
yeah, means they will give some combination circuit or something like that, and some constraints, and then we have to try to write the boolean expression for the what you can say, for the comparator or the adder. Means if it is
Okay.
given.
I just give you this question. I just give you this type of
Okay.
question. Just tell me you are asking the same question or not.
Okay, sir. Okay, sir.
Okay. So the question is that we have a 4 bit adder. Okay, we have a 4 bit adder. Okay. We have to perform operation A minus B when A is greater than B, B minus A when B is greater than or equal to. Okay, we have a 4 bit adder. We have to perform two operations. The operation is that we perform A minus B when A is greater than B, and B minus A when B is greater than A, greater than or equal to A. Can you try to solve it?
So you have to write the equations for that. Or,
Yeah.
okay.
I just give you 2 3 minutes.
So that 4-bit adder is for each bit, like for A 4 bits and B 4 bits.
Yes, have you done it? Anyone? Anyone have done it? Okay. The thing is that we have we required a comparator. So I'm just considering this is my comparator. Okay. There, this is the A data, B data. It is a 4 bit. Again, it is a 4 bit. And we are getting the A greater than B, A equal to B, A less than. Okay. Now we have a full adder, full adder, full adder. Okay. Full adder. Now when A is greater than B, so we have to calculate A minus B. So can I write it as A plus B bar plus 1? Okay. And if I say it is a B greater than equal to A, so it is a B plus A bar plus 1, because we have to implement a B minus A. So every time you see that it is a 1. Okay. So if I take either this one will be the 1 or this one will be the 1. Okay. Any of three will be the 1. So what I do, I just use one OR gate here, require one more OR gate here, and that I can use as a seed. That means C in is 1. Okay. Any case C in will be 1. So this one will be added. This one will be added. Any doubt? The second thing we have to implement that A plus B bar is remaining or B plus A bar is remaining. Now when A is greater than B, so this one. So we have A plus B bar. So what I do, I am using the A naught. Okay. And here I am using the XOR gate. B naught with this A B bar. Now recall the property of XOR gate. If any of the input is 1, we are getting a implement output. Okay, complement output. So if I apply a B naught and any of the input is 1, we are getting a B naught bar. So here we are getting a B naught bar. Okay. Similarly, we are getting in here Again, we are using the XOR gate. B1, and with B1 we are using again is same. Yeah. A plus B2. Okay. A greater than B. Similarly, we are using this one here. So we have A1, we have A2, this is that B2, and this one. Then A3, B3, and this one. Okay. So when A greater than B, we are getting as A plus B bar, and we directly add as C in as a 1. C in as a 1. So every time C is 1, so A plus B bar plus 1, we are getting A minus B. When A is greater than B. When A is greater than B.
So for c is equals to 1, we will add that a more than b and equal to b and then a less than b. Is that so?
Like for example, we have to add A minus B. So A is 0, 1, 0, 1, and B is what? 0, 1, 0, 0. Okay. So if 0, 1, 0, 0. So it is a 5 minus 4, we are getting a 1. Okay. Now how we implement this one? A as it is 0, 1, 0, 1. We are taking the ones complement of this one. So what is the ones complement? It is a 1, 0, 1, 1. Add these two. So 1, 1 becomes 0. Okay. We are carry 1. So 1 and 1 becomes 0. Carry 1, 1 and 1 becomes 0. Carry 1, 1 and 1 becomes 0. Now finally what we do, we are adding a 1. We are at a LSB, not for all. Okay. We are adding a LSB for 1 in a LSB. So 0 plus 1 becomes 1, 0, 0, 0. So it is okay. Any doubt?
Sir, means like the starting implementation of the scene that we have taken the we are what you can say added that a more than b and means a is equal to b.
Yeah. Every cases like for example A greater than B. Okay, A greater if A is greater than B, we have calculated A minus B. So A plus B bar plus 1 is there. If B is greater than or equal to A, B minus A, again we are getting a B plus A bar plus 1. So every case we have to add a 1. Okay, we have to add a 1. And we know in the case of comparator, either A greater than B is 1 and rest will be 0, or A less than B is 1 and rest will be 0, or A is equal to 1 and rest will be 0. Okay, so any one input will be the 1. So what should I do? I just use the OR gate. Okay, so that means we are getting always a 1 as an output. Now that 1 we are using as a seed.
And this the application is similar like for the a minus b, a plus b bar plus 1. So the adder will add that, no, what you can say, for b bar
Yeah, adder will get
we will XOR that b with the what you can say,
1. This one.
uh,
Which one? A greater than B. A greater
yeah,
than.
for a greater than b. So we will XOR
Okay.
for the b bar, no.
Yeah. So if B naught with 1, it becomes a B naught bar. If B1 becomes 1 in the XOR, it is a B1 bar. If B2 becomes with the 1 in the XOR, we are getting a B2 bar. And if B3 with the 1, we are getting a B3 bar. Similar to this one, we are doing the complement for all bits, not for the B0, not for the B1, not for the B2, not for the B3, all four bits. So we are taking the complement for all four bits. So that's why what I do, I just use the XOR gate. Okay, where one particularly input will be the one, and that one is what, A greater than B. So we connect A greater than B. Okay.
Yes.
Now second case is that A less than equal to B. Sorry, B less than B greater than equal to A. So now where B greater than or equal to A, B greater than equal to A is this point or this point. Okay, so I can just do one thing is there. I just use one OR gate for these two. Okay, then we use one OR gate for these two. Okay, there is no
That
issue.
will be that we will connect the XOR gate now for the A, no?
Yeah, we are connecting XOR gate from here. Okay. Now when B is greater than or equal to 1, so that means this point is 1. Okay, B greater than or equal to 1, this point is 1. Now we take the A bar. So again what I do, I just use one XOR. Okay. Connect this one with here, and this one is the A. Okay, again use this XOR gate, connect A1 with this one. Okay, with this one. Okay, use this one for all four. Now connect XOR gate A3 to this one. Connect XOR gate A2 to this one. Okay, so we have to convert. In one scenario, we have to convert B. We have to take a 2's complement, 1's complement of B, and then add 1. And say in the second case, we can take the complement of A. So for both input, we required a XOR gate. The situation is that for the B, for the B, we calculate the B bar when A greater than B. So what I do, I just connect a greater than B pin on the second input of the XOR gate. Okay, and for the A, B greater than equal to A, we have to connect a bar. So we just take a two particularly gate condition A equal to B, A less than B, XOR of this one. So that means this particular input is 1. Okay, this input is 1. Now use this one for the complement of A bar, complement of A. So what should I do? I use this particularly as an input for the one XOR gate where A naught is connected. Clear?
Yes, sir.
Now from here we are getting the S naught, S1, X2, S3, C out, Okay, C3, okay, C2, okay, C. Okay, so this is basically about the combinations. Now, if you have any doubt, you can ask. Yes, any doubts? Any question related to the week 4 to week 8?
Sir, regarding the BCD to binary conversion,
BCD to binary conversion.
yes, we know that from the number is more than the nine, then we add the six,
Six.
and
Yeah,
if it is not, then we add zero only.
yeah.
We get that BCD term.
Okay.
Yeah, but like the questions are little bit twisted, no? So if possible, if means you can show that, like, how to deal with that.
Hmm. How we implement that one you are asking, or basically some questions related to that one?
Yeah, if yeah, related to question only for
Okay.
this and for the adder also.
If you have any questions like where you are facing any issues, so you can ask
Like
questions
in
related
the quiz two only,
to. Mhm.
uh, I didn't got the solution, sir, because it is the only answer key that I have.
Okay.
Means the last four questions were like difficult to solve in the quiz two.
Okay. Just let me check. So I think you are asking about the comprehensive.
Yes, sir.
Okay.
Like how to tackle these questions.
Okay. So the thing is that there are three particularly circuits or three figures are given. Okay, figure one, figure two, or basically the figure three. Okay. The question is design two combination circuits, circuit one and two, in which the circuit one perform the addition of the two bits unsigned binary number, each 2-bit long, and circuit to perform the customized decoder that accept the output Cout S1 and S0. That means this particularly is the combination. Okay, and with respect to this one, it will be the A, B, C, D, E, F, and G. Okay, seven are the basically lines giving as the output. Okay, now if we are saying that if we connect A in this one mux, B in this one, C in this one. Okay, so we have a mux where four inputs are given. With respect to this one, we are getting a one output. Okay, and one output is like, for example, if we use this in place of this circuit, if I am using this circuit 3, okay, if we are using this circuit 3 where S1 and S0 are the select line, okay, and input is P0, P1, Q0, Q1, because P and Q, okay, P and Q will be the 2-bit data, so that means P0, P1, P0, P1, so 4 data, 4 input will be there. Okay, and with respect to this one, if I use this A, B, C, D, E, F, G for the 7 segment display, okay, so there are the 7 segment 1, 2, 3, 4, 5, 6, and 7. So we use this 7 segment display with the help of this 7, okay, output pins. Okay, so this is the questions. Like if we replace this particularly circuit with the circuit 3, okay, and we are using the A, B, C, D, E, F, G, and that we use for the 7 segment display. Okay. Now the question is that select the Boolean expression S naught for the of the circuit. Circuit one. Okay. The what is the S naught? If we are taking P and Q is a single bit data, so S is the single bit output. Sum.
It
Okay.
depends on P0 and Q0, no? So that's
Depend
why
on P0 and Q0. But what is the equation for the sum?
that is we do XORing of that.
XORing of that one. So P XORing Q. Okay, if we are talking the S naught, so it is a P naught XORing with Q naught. If we are talking about the P1, so P1 is the P naught P1 XORing with Q1. Okay,
Yes.
now they are asking what is the Boolean expression for S naught. S naught is what? P naught XOR with Q. The Boolean expression for the sum. Okay, now second, select the Boolean expression to see out of the circuit one. Now when the C out will be the one. So can I draw the truth table here?
Yes, sir.
Okay, so if I write the table for C out, okay, so basically we have a P naught, P1, P naught, Q1, Q1. Okay, so with this we are getting a four input. So with the four input we are getting a 16 combination. 0 0 0 0 0 1 0 0 0 0 1 1 0 1 0 0 0 1. Okay, and so go here. P1 P naught Q1 Q. So 0 0 0 0 0 0 0 1 0 0 1 0 0 0 1 0 1 0 0 0 1 0 1 0 0 1 1 1 0 0 0 1 0 0 1 1 0 1 0 1 0 1 1 1 0 0 1 0 1 1 1 0 1 1. Okay, so now initially we add a P0 and Q0. Okay, and if it is carry will be generated, so P0 and Q0, no carry, no carry, no carry, no carry, no carry. Here the carry is generated. Okay, internal carry is generated, but this internal carry will be forwarded to the P1 and Q1, so the C out is 0. Now no carry. Here carry is generated. Okay, carry is generated, carry forward to here, so 1 and 1 becomes a 0 and carry out is generated. Okay, LSB will be added initially. If carry is generated, it will be added to the LSB. LSB is added, LSB is added. Now here 1 and 1. Okay, LSB is 0 0, so no carry forward, but MSB is 1 1, so carry out is generated. 1 and 1, carry out is generated. Now 1 and 1, 0 carry is generated, and this carry will be added in the MSP. So 1 and 1 become 0, so carry is generated. Carry is generated. 1 1, 0 carry is generated. 1 and 1 with 1. So 1 carry is generated. Okay. Now you can write a K-map. With the help of K-map, you can write a expression for CO. Okay.
So when means the MSB is one, then the carry out here is one.
If MSB is 1 1, then carry out is 1.
Um,
Wait a
but
minute.
if the LSB is one one,
If
then
you
it
see,
goes.
if you see that if MSB is 1 1, then carry out is 1. So if MSB is 1 1, MSB is uh, MSB is 1 1, MSB is 1 1. Okay. So when MSB is 1 1, carry out is 1. Okay. So
When the
MSB
LSB
is
is one
meaning
one,
is P1 and Q1. This is the one condition where where carry will be generated. Okay.
and when the LSB is that LSB is one, then it goes internally
Yeah. When LSB is 1, it is going internally.
and gets added in that what you can say in LS and MSB.
Yes.
Okay.
Okay. Now second condition is what? When LSB is 1 1, like in this one. When LSB is 1 1. With respect to the MSB, either P is 1 or Q is 1. So when LSB is 1 1, so that is P naught Q naught with either P1 or Q1. Okay.
So either it will go with P1 or Q1.
Yeah. Either P1 is 1 or Q1 is 1, and the LSB is both LSB is 1. Like for example, 1 0, sorry, 1 1 0 1. Okay, so 1 1 will becomes a 0. 1 carry is generated. 1 0 is 1, and this one becomes 0 and carry out is 0. Okay, this is the one case. Second case is that 0 1 and 1. Again 1 1 becomes 0, carry is generated. 0 and 1 becomes 1, and this one will be added, so it is a 0 and carry is generated. So if it is a P1 P 0 Q1 Q 0, so Q 0 is 1, P 0 is 1, so P 0 and Q 0 is 1. And the second thing is either P1 is 1 or Q1 is 1. Okay, so we are taking the P1 and Q1, either P1 or P2.
Yes, sir. Got it.
Okay, so if you see that P0 Q0, P1 Q1 is the first term, second P0 Q1, either P1 is 1 or Q1 is 1. Either P1 is 1 or Q1 is 1. So this is the three particularly possibilities where carry out is added. Okay, that's clear. Any doubt?
No, sir.
So this particular is now identify the logic state of the output lines in circuit 2 when P, Q are in their maximum value. So P is the 2-bit data.
That was 6, no?
Yeah, Q is again 3, 2-bit data, that is a 3. So if we add a P plus Q, it becomes a 6. Okay, so 6 is what? If you see here 6. So in
All
this
are
A
1
is
and
generated, B is 0, and all are 1. Okay, so A is 1, B is 0, and all are 1. This is the correct answer. Okay, now select the Boolean expression for the output line C in the circuit second, which receive input from the output line of the circuit. Okay, C. So where is the C? C is this third pin. Okay, so this third pin will not, C is 0 for 2, for only 2. When 2 is displayed, C is 0. Otherwise, C is always on. Okay, any doubt?
for 2 the C was 0, except for other it was 1.
Yeah, always 1.
Okay.
For only 2, C is 0.
Yes, got
Okay, so what is the meaning of 2? It is a 0 1 0. So C out S1 and S2. Okay, so for this one it is a 0. So what is the max sum from that one? S0 plus S1 bar plus. Okay,
Yes, sir.
Because for 2 it is 0. So in the case of 0, when we consider the logic 0, we have to identify, we have to use the max sum. Okay, so write down the 0 1 0 max sum for the 0 1 0 for 2. So it is a S0 plus S1 bar plus C now. Now select the correct option for segment C of the common cathode in the order to input line marks 0, 1, 2, 3. So we have a 4 cross 1 marks. Okay, where we are using S1 and S0 as a select line. Okay, now we know that C line will be the C is on when we display 1, 3, 4, 5, 6, 7, 8, and 9. Okay, but we have a 3 input. Okay, we have a 3 input, so maximum we can display as a 7 till 7. Okay, so C is on for 1, 3, 4, 5, 6, and 7. And C is off for
Two.
2. Okay, so we are taking the S1 and S0 as select line, so it becomes 0, 0, 0, 1, 1, 0, and 1, 1. And C is 0 and C is 1. It is a 0, 0, 0. It is defined. It is a 0, 0, 1. It is defined. Sorry, 0 also. Okay, 0, 1, 0, 2. It is not defined. 0, 1, 1, 3. It is defined. 4, 1, 0, 0. It is defined. 1, 0, 1. It is defined. 1, 1, 0. It is defined. And 1, 1, 1. Okay, so when S0 is 0, 0, I naught is selected. The value of I naught is the group of this. So this is not. When S1 S naught is 0, 1, this group again 1. When it is a 1, 0, so in this case it is. So the C naught is 1, so it is a C. Okay, and when it is a 1, 1, again a group of these two. So, again. So 1, 1, C out and 1. Okay,
Yes, sir.
so any other doubts? So I think we will we recall the week 1 to 8 content. Okay, just go through with the content again. If you have any doubt, we will solve that one in the next class. In the next class, we go with the 9 to week 12. Okay, that is the sequential cycle. Okay,
Yes, sir. Good night.
yeah. Thank you all.
Thank you. Can we expect such same questions in the interview?
Thank you, sir.
Yeah, what you are asking?
Can we expect such questions in the same questions in the end term also?
Uh, Not that same.
No, not that same. It's not possible. Because
Somehow similar.
yes, it is little different, a different kind of question there for the quiz
Mhm.
two. Because such
Somehow
questions was
similar.
already in the not only in the graded assignment, so it's
Oh,
little different there.
okay. So somehow similar with the quiz two, you can say that.
So it is such like that is a like practical example that you are just
Mhm.
introducing the seven segment LEDs, so you have the idea of how seven segment LEDs and all that and everything.
Mhm. I think you are using the 7 segment LED also. That's why we are doing this question in the quiz.
Pardon?
You are using the 7 segment display, na, in your practical part.
Yes, yes. In the lab,
So
I think.
that's why, yeah, in the lab. So that's why we are giving this particularly for this type of question 7 segment display in the technology because
Hmm.
it is not. I think it is not covered in the theory part.
Right,
In
right.
the lab, you are using the 7 segment display. So we are related this particularly. Our basically purpose of this one is that we are basically corporate or basically we are using the encoder and decoder circuit with the 7 segment display. How we use
Right,
the encoder and decoder circuit for the 7 segment display.
right, right.
So to combine these two theoretical and practical knowledge, we are giving this question in
Yes,
the
yes.
quiz two. Okay, the anthem is also similar to this one.
Okay,
Okay, there are some questions we have to think about that one. Okay,
okay.
and I think you have a sufficient time this time. Anthem.
Yeah, 3 days only. Sunday.
Yes.
Prepare it and revise and all of this.
Yes.
All the weeks. Okay, thank you. Good night.
Okay, good night.